Hi, let me tell you about another great Manning book, The Hughes List, Fabulous Adventures in Data Structures and Algorithms, written by Lippert.
Hi there, I'm Lippert. In my new Manning book, Fabulous Adventures in Data Structures and Algorithms, I'm going to take you through some of the weird, wonderful data structures and algorithms that change the way I think about programming. And in this video, I'm going to talk briefly about one of the topics in the book, the Hughes list. The usual implementation of a stack is a linked list. A stack is either empty or it's a value with a link to its tail. If we pushed 9, 0, 3, 5 onto an empty stack of integers, we'd get something like this. The asymptotic performance is clear from the code. Pushing the head, popping the head, peaking are all constant time. But reversing a stack, concatenating two stacks together, and appending an item to the wrong end of the stack are all linear time. We can have a helper method, reverse onto, it's linear, and with it we can write reverse, concatenate, and append. The Hughes list turns all of that performance on its head. In a Hughes list, peaking and popping takes linear time, push, append, and concatenate are all constant time. And even stranger, the Hughes list appears to contain no data at all. Its only member is a delegate to a function called concat that takes a stack and returns that stack concatenated to some other stack. So how could this possibly represent a list? Well, we can start by looking at the empty Hughes list. What does concatenating an empty stack onto any stack do? It just returns that stack. The empty Hughes list is the identity of concatenation, so the identity function is the empty Hughes list. What about a non-empty stack? The Hughes list of a stack is a delegate to its concatenate method. We get the original stack back by concatenating an empty stack onto it. The key to understanding the Hughes list is the concatenate method. If you have two functions that both concatenate stacks, then their composition is also a function that concatenates stacks. Calling concatenate does not execute the concatenation. It creates a function that does so later, and that function is the Hughes list. And that operation, creating a function, takes constant time. This method, single, produces a one-item Hughes list. It's a useful helper. We need a function that concatenates a single item to a regular stack. But that's just push. So now that we have a constant time concatenate and a constant time single, we can implement constant time push and append. They just concatenate single items onto lists onto opposite ends of the stack. So far, everything that we've done with the Hughes list has been constant time. Hughes lists have no constant time pop or peak operation. The best we can do to pop or peak is convert back to a regular stack. That executes all of the deferred operations in the functions, and those can be linear in time. We get constant time concatenation by deferring the cost until toStack is called. But what explains the miracle of a data structure that appears to contain no data? The key is in the bolded parameters here. When a variable declared outside of a lambda is used inside it, the compiler secretly creates a data structure for you called a closure, and it remembers the values of those variables for you. Single creates a closure that remembers what item to push. Concatenate creates a closure that remembers which two lists were concatenated. So Hughes lists are secretly binary trees. If we push 7, 6, 8 onto one Hughes list and 9, 0, 3, 5 onto another, and then we concatenate those two Hughes lists together, the data structure in the closure behind the scenes would look something like this. It looks like a binary tree, and now it's clear where the data is. The Hughes list is really good because it's a fast way to build up one large list out of many smaller lists by concatenating items together onto either end or concatenating sublists together, as long as you don't need to read the items out of any list until you're done building the big list. Learning how the Hughes list takes advantage of closures to secretly make a binary tree of deferred operations gives us a new way to think about what compilers can do for us as developers, and that's the really fabulous thing about this data structure. I hope you enjoyed the glimpse into the world of fabulous data structures and algorithms. The book covers this in much more detail and also explores topics as varied as combinatorics, category theory, stochastic programming, code analysis, graph coloring, and much more.
Get this book at manning.com.